Now let us come to the causality of the C element. For the C element, let's consider a spring. And say one end is end A, the other is end B. And we assume that there's a velocity at the end A, VA, and the velocity at the end B is VB. And naturally, because these velocities are going to be different, we'll have relative velocity between A and B. Now, the rate of change of deformation that is caused due to this relative motion, it will be VA minus VB. Okay, and that we can write as we can have this C element, which represents compliance, not stiffness, but compliance, which is the inverse of stiffness. Okay, so we have the effort variable and we have a flow variable. The input to the system is the change in displacement with respect to time or flow. Okay, what a spring does is it takes motion across, it takes deformation, rate of change of deformation across its ends, and then it integrates this to obtain its state. Its state is generalized displacement Q. So this C element, it integrates the flow, determines Q, and then produces an output which is a function of Q. Okay, so the output or the effect has to be a function of its state. This is the property of a C element. You can see that the C element can take deformation. You apply, you can deform it, deform its ends. But the force that you experience while deforming it, that is determined by the spring, the character of the spring. Just as a simple example, you can hold a small spring. Imagine holding a small spring between the tips of your fingers. Say, consider you must have seen the ball pen spring, okay? Ballpoint pen spring. So just consider that, and you give it motion. Okay, move it, deform it by, let us say, 1 centimeter. Okay. On the tips of your fingers, you will experience a force. Now imagine that this spring is harder. It's more stiffer. And you are going to apply the same deformation, okay, across its ends. What is the force? What is the magnitude of the force that you will experience? Can you tell me? What is the magnitude of the force that will be experienced for the same deformation if the spring is harder?
So K into X.
Yeah, that's right. I told you already, it is a harder spring. So what will happen? Will it experience more force or less force for your fingertips in order to deform the harder spring by the same amount? Will the force experienced by the fingertips be less or more?
The
More,
more.
sir. More.
Sir, more, sir.
More, sir.
Why more?
So because
Because
of spring cost.
Spring is stiffer.
yeah, it is because it is the spring's property. It is the spring which is determining what should be the effort. It will decide the effort. You are deciding the flow. You are deciding the deformation across it. But it is the spring which will decide based on its characteristic what is the effort. Okay, so it will decide what is the effort. As simple as that. Okay, it will take the deformation, integrate it. It will take the rate of change of deformation, integrate it, obtain the generalized displacement, In this case, it is the deformation, and then it will provide a force which is a function of this deformation. If the spring is linear, then as you said, K into Q. So you will get the force that is linear. But if it is a non-linear spring, it could be a quadratic, it could be a polynomial spring. So in that case, most of the springs in nature are non-linear. Okay. In a very vast range, they may behave linearly, but then throughout the range, they are not linear. So the relationship again goes the same way. The output, that is the effect, that is effort in this case, is a function of the generalized displacement, which is the state of this C element. And in this linear spring case, it is just K into Q because it's a linear relationship. Force is directly proportional to the deformation. And that is equal to K multiplied by the integral. How did you get this Q? The state was obtained by integrating this cos, integrating Q dot with respect to time. So you integrated this cos, which was the flow, okay, right up to the present time, and obtained the state, and then produced an output which was a function of the state. So that is what happens actually for springs. We can also write it in this manner. It's the natural or integral causality for the C element. You see, for the I element, integral causality, causal stroke was here near the I element. But for the C element, the causal stroke is away from it like this. Okay, this is the natural or integral causality for the C element. Now let us consider the C element in derivative causality. Now, in derivative causality, we take the spring, okay, the same relations, but now instead of flow being the input, the effort is the input. And it's the input or the cause. What the spring is required to do is determine its state. It has to determine Q by inverting this relationship. If it is invertible, then fine, it can determine it. Not if it is not invertible. Okay. So let's assume it is invertible, it can do that. But then after that, it has to produce an output effect, which is the derivative of the state. Okay. Again, the same problem as we had in the I element. Derivative does not take into account the past history of the cause. And so you will see that it cannot take into consideration past history. And so this is not the natural causality for the C element. Okay. When the causal stroke comes here, that means there is a violation of the C element. There is some problem with the C element. It should not come like this over here. Okay. Then now that we have discussed the C element, the cause and effect, let's take some more examples before we proceed to the R element. I have some examples here. Yeah. So this is what we have already discussed. You see, in this, the nature of the I element. Now we come to the constitutive relations for the I element. The nature of the I element is such that there is a relationship between the momentum and the flow. So the flow, which is the output, is a function of the momentum. Okay. In Newtonian mechanics, this function is very simple. It's a line. It's a simple straight line. Flow is equal to P upon M. Okay. And you can see that if you just integrate this, you will be getting what we call as the kinetic energy. Okay. kinetic energy of this mass, change in the kinetic energy will be obtained. So if you want to determine the kinetic energy, you just have to integrate, as we discussed in the previous lecture. You just integrate it and you get the kinetic energy in the mass by virtue of its motion. Then we have another example of an electrical inductance. Now for the electrical inductance, this is a device which is due to windings of conductors. Okay, so motor windings, transformer windings. These are devices, coils. They have inductance. So in that case, there is a current or flow which passes through this conductor, and there is a flux linkage associated with it. Okay. Now this momentum in this case is physically the flux linkage associated with this winding. And you can write it in terms of, if it is a linear relationship, you can write it as L into I, where L is the inductance and I is the current through the coil. Now, in that case also, it's very simple. It will accept the voltage that is applied across it, which is changing its electrical momentum or changing its flux linkage. It will integrate it and determine the electrical momentum or the flux linkage, which is commonly written as lambda. And then it will produce an output, which is a function of this state, function of the electrical momentum, that is lambda upon L, okay, which is the current. So the inductance actually determines what is the current. It is its property. Depending upon its nature, depending upon its inductance value, it will specify what should be the current that should flow through it. Okay, you can apply voltage across it, but it is the inductance which will determine what should be the current that should flow through it. So the effect is a function of the cause, a function of the integral of the cause with respect to time, right up to the present time. This is how we can view the causality, the constitutive relations and the causality for the electrical I element. Here, of course, we need not consider it to be linear only. It may be non-linear as well. We have taken it as a linear inductance though, but it can be non-linear as well. Here we have this example in Newtonian mechanics. You see, the mass is directly, the momentum is directly related to the velocity. Okay, the state, which is momentum, is directly related to the output, which is the velocity. And it's a straight line relationship. That is in Newtonian mechanics. But the moment you switch over to relativistic mechanics or relativistic motion, which takes place at higher velocities, okay, there you find that the velocity, it is capped by v naught, which is the speed of light, the velocity of light. And so the momentum, it changes. The rest mass multiplied by the velocity divided by square root of 1 minus v by v naught square. Okay. So in that case, it is linear. This relationship is not linear. Okay. Unlike the Newtonian mechanics where you had a linear relationship. So the point that I want to make is, it doesn't matter whether the relationship is linear or non-linear. What is important is the relationship between momentum and that is the flow. Okay.